Hi, today we're going to help you explore PHET's interactive simulation called Sugar and Salt Solutions to learn about intramolecular forces and what happens when different types of compounds dissolve in water. We can begin at the macroscopic level here. This is what we see with our eyes. Let's add some salt to the water. When the salt crystals dissolve, we can no longer see them, and although it looks just like plain water, you would definitely still know the salt was there if you took a drink. We call this type of mixture, where you can see only one phase, a homogeneous solution. Let's select the sugar and add some of it to the liquid. Again, notice how there are no visible changes to the water. Based upon what we can see at this level, both sugar and salt seem to have the same physical properties when mixed with water. Now we're going to hit the reset button and remove both salt and sugar from the solution. Next, we put the conductivity meter in the water. Notice how the light bulb here is not lit, which means that the water is not conducting electricity. Take a moment and predict what you think will happen to the conductivity of the water if we add in sugar. Notice how nothing happens to the conductivity of the water when the sugar is added. Take a moment and predict what you think will happen to the conductivity of the water when we add salt. Let's see what happens. See, the light on the bulb glows when we add the salt. Notice that the light rays grow, indicating the intensity of the light is stronger as more salt is added. So why did the salt conduct electricity when dissolved in the water when the sugar did not? They must be different. To see these differences, we need to examine this at a particular level, indicated here by the microtab. At this level, we can understand the differences that arise between salt and sugar when dissolved in water. When we pour salt in the water, notice how the sodium and chloride ions separate from each other. Having these charged particles, positive and negative ions, able to move about in the solution is what leads to conductivity. Now let's remove the salt and add in the sugar instead. Notice here at the particulate level that the sugar molecules do not break apart, unlike the salt. Instead, the carbon, hydrogen, and oxygen atoms are held together by covalent bonds. Sugar doesn't lead to conductivity because the molecules do not break up. Only neutral molecules are present here in solution. Now let's take a look at how both of these compounds interact with the water at the particulate level. Wow, there's lots of movement here. So let's pause the simulation for a moment. These molecules represent the water. The red indicates an oxygen atom, and the white indicates the hydrogen atoms. And if we see each molecule has one oxygen and two hydrogens. It's important to know that water is a polar molecule, which means that one end of the molecule is slightly positive, the hydrogen end, the white end, and the other end is slightly negative, the O end. We can show this by clicking this little box down here. If we look carefully, we'll see that most of the time, the hydrogen will be attracted to or pointed at an oxygen atom on another molecule, that the delta plus is interacting with the delta minus. Remember, opposites attract. Now, let's remove the partial charges and restart the simulation. Let's add in the salt, and then we can pause the simulation to see what's happening. Right away, we notice that the ions all started to separate. But if we look a little more closely here, what we will see around the sodium is that we have a whole bunch of red oxygen atoms that are all pointed towards it. So why would this be? Well, let's go back to our partial charges here. Our sodium has a plus charge, and remember, all of our oxygens have that partial minus charge, so they're all pointed at the plus. Now we're going to remove the salt and add the sugar to the water. Notice how the sugar doesn't break up like the salt did. So why is that? Well, let's look a little closer. The sugar molecule actually has many OH groups which have similar positive and negative charges just like the water. This allows the sugar molecule to interact favorably with water through hydrogen bonding. We can see this better by removing the yellow coloration of the sugar molecule. Now we can clearly see the white hydrogen atoms attached to the red oxygen atoms, such as right here, or here, or here. Thus, the sugar is attracted to the water just like other water molecules were attracted to each other. However, the very strong covalent bonds in both the sugar and the water remain intact, meaning that both molecules are neutral, so the solution does not conduct electricity. I would encourage you to further explore the simulation, as there is quite a bit more to discover. In particular, it is worth noting that there are a number of different solutes that can be explored by clicking through the options here. You can find and download the simulation at the PHET website shown on the screen. Thanks for listening, and enjoy exploring the simulation.